All right, so good morning, everyone, and good afternoon, good evening, depending where you are. Welcome to this new Landscapes Live seminar series. Today's speaker is Eric Deal from ETH Zurich, and he will be talking about cell-formed channel with emergent channel width and sediment transport. We will take questions as usual near the end of the talk, and we will just open the chat when we will reach the end and we will read your questions. You can also raise your hand to ask your question directly. And Eric, the floor is yours.
Okay, great. Thank you very much for having me. I'm really excited to talk about some of the stuff that I've been working on for the past few years, which is all about self-formed channels and hydraulic geometry. But before I get into that, I just want to talk about what's motivated my work on channel hydraulics. And that has all to do with an intriguing puzzle relating surface topography to surface processes. So, trying to change. There we go. So I'm going to talk about this in the context of collisional origins, which is an ideal testing ground for theories of landscape evolution and tectonic geomorphology. And in these landscapes, convergent tectonic motion generates surface uplift, which creates a gravitational gradient that drives in turn surface erosion. And this is a self-regulating system that tends towards the point where the surface uplift rate is equaled by the surface erosion rate. And at this special point, there's termed dynamic equilibrium or just steady state. The topography becomes a reflection of the tectonic and surface processes that are creating it. And by topography, so I'm going to skip a few steps, and really by topography, I wanted to say the topography reflects the surface and tectonic processes, and this opens the door to this idea that we can infer something about the tectonic and surface processes in the landscape just by looking at the morphology of the landscape. And I'm going to skip a few steps and say it's not just the landscape morphology in general, but specifically the morphology or the topography of the river network in these landscapes. And so here I'm showing sort of a steep mountain river basin where the topography or the elevation is shown with the color, and the river network has been outlined in blue. And the reason we focus on the river networks is because we think they're the rate setting process. So the sediment transport and the bedrock incision by rivers is the rate setting process for erosion surface processes in these landscapes, and the hill slopes are sort of just following along. And more specifically, it's not just the surface topography, which is sort of linking this erosion rate to, it's not just the link between the surface topography and the erosion rate, but specifically the channel slope. So before I talk about the link between erosion rate and channel slope, I just want to discuss the channel slope a little bit more detail. So we can get at the channel slope by looking at like a single strand of any particular strand of this river network, and then stretching it out and plotting its elevation as a function of the distance along the river. So we get what's called a long river profile, and they tend to have this concave up morphology. And in fact, we know that morphology comes from the fact that the catchment area or the contributing area is increasing as we go downstream. So in particularly in steady state landscapes, what we see is that the product of the channel slope and the contributing area to some exponent is equal to a constant. And so if we increase the contributing area downstream, then we have to decrease the channel slope to accommodate. And the reason that this matters is because if we're trying to relate channel slope to surface processes, we're looking at the Blue River, for example, is on average clearly steeper than the Yellow River, but the channel slope at any one particular location is not necessarily steeper than the channel slope at any particular location in the Yellow River. So to accommodate, sort of account for this changing river slope and allow for intercomparison of slope at different parts of the river network, people have developed what's sort of an area normalized channel slope, which is called the channel steepness. So I'm not going to go into all the details, but if you normalize the channel slope by the catchment area, you can plot sort of these normalized river profiles, and you see they plot as straight lines in this normalized space, and the slope of the profile at any location is just this channel steepness. So the steepness is then like an intercomparable measure of the slope of the channel. And really then, to be specific, so I'm saying that looking at landscape evolution and processes in these steep, rapidly uplifting collisional origins, we can sort of try to relate the topography of the river network to the tectonic and surface processes that are forming that landscape. And specifically, we can relate the erosion rate to the river steepness. And so this is sort of a concept or a hypothesis that's become quite important in geomorphology and tectonic geomorphology, that the erosion rate of the river, and therefore by extension the whole landscape, is some nonlinear function of the channel steepness. So channel steepness is some exponent n. And there are a number of ways that you can sort of look at this and convince yourself that that's true. And I'm not going to go into all that. I'm just going to show one data set here, which is plotting the basin averaged erosion rate of a number of landscapes in the sort of collisional setting I'm talking about, and against the basin average channel steepness. And you see here's sort of a positive correlation between them, implying that perhaps it's the increase in the channel steepness that's driving these observed increases in channel erosion rate. And this has come to be really a fundamental tenet of tectonic geomorphology. And so here it influences how people interpret river profiles. So here I'm just showing an example river profile with two different sections of different steepnesses. So the blue section has a low steepness separated by a nick point from the red section of the profile that has a high steepness. And this is interpreted as resulting from different erosion rates in the two sections of the river profile. This idea that erosion rate goes with the river steepness also underlies important landscape metrics such as chi, which is also used for interpreting river profiles, but other things like measuring basin disequilibrium. And it's absolutely fundamental to all of our landscape scale, landscape evolution models. As I'm honest, I don't really know how you would run a landscape scale model if you couldn't say that the erosion rate was proportional to the channel steepness in some way. Finally, it's sort of critical to our understanding of how tectonic and climatic signals and changes are propagated throughout the landscape, tying into things like the response timescale of landscapes. So overall, this sort of simple looking equation really encapsulates our understanding of how landscapes evolve and operate in these steep collisional settings. And it would be problematic if it turned out to not hold in certain places. But this is exactly what we're seeing in some recent data sets. So here I'm showing a data set from Hilly et al. In 2019, where they found a range of basins around the world spanning a very large range in measured erosion rate, so 3 orders of magnitude, but they were chosen for having relatively uniform lithologies and climates to sort of minimize confounding variables. And what we see is that at low erosion rates, so the data, each basin is sort of the black point here, it's plotting the channel steepness against the basin average erosion rate. And so at low erosion rates, there's a relationship between the channel steepness and the erosion rate. So as we increase the channel steepness, we're also seeing an increase in the erosion rate, sort of outlined with this blue trend. But then at some point, this relationship effectively breaks down, and we see that there's a 2 order of magnitude change in erosion rate accompanied by almost no change in the channel steepness. And so that's here captured with this yellow trend. And our research group has been looking into this a bit. We've collected sort of a similar larger data set. These are all granitic basins, but we haven't controlled for climate here. But we still see a similar pattern. So the actual fit exponents are not as dramatic, but the same pattern holds that at low erosion rates, there's a correlation between channel steepness and basin average erosion rate. But then at higher erosion rates, we can have an erosion rate over almost 2 orders of magnitude range with effectively the same channel steepness. And what this is really a decoupling of topography and tectonics. So if we're talking about steady state landscapes, we can increase the tectonic uplift rate, the surface uplift rate by a factor of 100 and not see any response in terms of the river network morphology, or at least any response that we understand. And this is something that I've been paying attention to for the last few years and trying to see if, how widespread it might be. And here I'm just showing the same pattern that I've found in several other places. So this is not my data. These are other people's data that I'm showing here, where again, I'm plotting in all 4 plots the channel steepness as a function of the basin average erosion rate. And in Taiwan and the lower Himalayas and the greater Himalayas, as well as the greater Caucasus, we see this pattern of a correlation between steepness and erosion rate at low erosion rates that then breaks down to some degree at higher erosion rates. And I'll just point out that in the case of the greater Caucasus, the authors of this study, they have drawn a sort of a picture of this breakdown being caused by discharge variability, and that may very well be the case there, but using discharge variability depends on sort of specific climatic patterns, and I don't think it can be used as a general mechanism to describe this breakdown, this decoupling of tectonics and topography in a more global sense. Okay, so this slide is just kind of summarizing the results that I showed in the past few slides, where I'm showing the exponent, the best fit exponent at low erosion rates in blue for these 6 different data sets, and then the best fit exponent at high erosion rates in yellow. And you can see at low erosion rates, what we see is not a sort of linear or modestly non-linear relationship between erosion rate and channel steepness, such that as we increase the erosion rate, or really increase the uplift rate, these channels are responding by changing their slope, by increasing their slopes. But then at higher erosion rates, the relationship is often very nonlinear, suggesting that there's a sort of a decrease in the sensitivity of topography to tectonics at these high erosion rates. And so the picture I'm kind of trying to paint here is that at low erosion rates, the erosion rate is increasing as a function of the channel steepness. So the river network is encoding information about the tectonics of the region, and the increases in channel steepness are what's driving these higher sediment fluxes and higher bedrock and erosion rates in the rivers. And then as we transition to higher erosion rates, this relationship fundamentally changes. And rather than responding to increases in uplift rate, and requirements for higher sediment fluxes and higher erosion rates by increasing channel slopes, it's something else that's happening in these landscapes. And I don't necessarily have the answer. I think that you could come up with several possible explanations for this, but I would just point out that it's fairly important to understand, what's going on. If erosion rate is not a function of channel steepness, what is driving it, and how do we modify our understanding of how these landscapes are operating at high erosion rates, and what is really changing to cause this shift in behavior. And I personally don't think that we're going to be able to answer this question by looking at more channel steepness data or more erosion rate data. And I'm in favor of taking a closer look at what is going on inside the channels themselves, and so the channel hydraulics and how that's operating. And so that leads me then to the topic of my talk, and really the work that I've been doing over the last few years is looking at hydraulic geometry. So channel hydraulic geometry is a tool to understand these fluvial incision processes in these larger temporal and spatial scale patterns that we see. And so the hydraulic geometry is just sort of a set of related variables that describe the shape and functioning of a channel cross section. It includes the water flux Q and the sediment flux QS, as well as a characteristic grain size and a mean velocity. So one velocity is representing the average velocity of the entire river, U. And then the channel slope, S, which is the same channel slope that I've been talking about so far. and a surface width W, and finally some mean channel flow depth, so one average flow depth for the whole channel H. And I don't know if everyone would agree with this, but the way I kind of conceptualize it is that the water and sediment flux and the characteristic grain size are the imposed variables that the channel has to deal with. And the flow depth, velocity, width, and slope is sort of the geometry of the channel that it can choose in order to accommodate these imposed fluxes. And there are just a couple other, I think, important elements to cover talking about hydraulic geometry. First of all, like the discharge is an element of the hydraulic geometry, but rivers have lots of different discharges. Discharge changes from day to day as they ebb and flood. Really what I'm talking about is the discharge most responsible for forming the channel. So this is often referred to as, generally referred to as bankfull discharge. It's fairly well understood, at least in alluvial rivers, and it typically comes in at significantly larger than the average discharge of a river. So going forward, when I talk about hydraulic geometry, I'm really talking about bankfull hydraulic geometry. And the second element that I think is really critical to having sort of a conceptual model of hydraulic geometry is that the erosion rates, is that you have a steady state cross section, so that the cross-sectional form of the channel is not changing in time. And then you can meaningfully relate the imposed variables to the response variables of the system. And we can meet this criteria by imposing that the erosion rate of the channel boundary is a constant. So it could be positive or it could be negative. It could be an incising channel. It could be a depositing channel. It could be zero. The channel is not really doing anything, but it has to be constant across the boundary. For example, if the erosion rate were higher in the center of the channel, we would, at some point in the future, leave the sides of the channel behind. We would change the channel form, and we wouldn't really be talking about a steady state channel geometry. This ends up being a really restrictive set of constraints. Once we impose these mass fluxes that the channel has to convey with the grain size as a boundary condition, and then impose that the boundary has to erode at a constant rate, the channel is pretty restricted in the possible orientations it can take to solve that problem. And it also helps to relate then the fluvial erosion processes that we think about at the landscape scale to this more fine-grained, discharge, big bankfull discharge, grain size, local channel geometry. One thing I think is an advantage of looking at channels this way is that we don't need to worry about landscapes being at steady state or not, because the time it takes for a channel geometry to reach steady state is far shorter than the time it takes for the landscape to reach steady state. So we can have channels, river profiles that are transient, but have channel cross sections where each cross section is effectively at steady state. And I think the main advantage of this approach to sort of interrogating fluvial incision processes is that there are far more data. The boundary conditions can be more carefully, constrained, and there are more variables to look at. So it just offers a more rigorous test of any theories or understanding of how these rivers are working. So in the spirit of testing hypotheses, I just want to introduce the data set that I've compiled to sort of, talk about these ideas. So here I'm looking at mostly bankfull hydraulic geometry. This is compiled from a lot of other data compilations, and I'm going to plot the 4 response variables, the channel width, the channel depth, the channel flow velocity, and the channel slope as a function of the non-dimensional discharge. And so, in fact, all these parameters are non-dimensional, and they've all been non-dimensionalized by the characteristic grain size D. So this is the data set. Each individual colored point is a channel reach. There are about 3,000 channel reaches, and each black point is the logarithmic binned median value with the error bars representing one standard deviation within each bin. I think the first thing about this data set is that we should all be kind of blown away that all these different rivers from all over the world, really mostly just from all over the US, but still it's a very big place with lots of different climates and conditions, they all pretty much fall on the same trend. So, the river width and depth, they all kind of fall within, for a given discharge, the same restricted widths and depths. This is just sort of revealing how incredibly constrained these channels are by these imposed conditions, and how strong the feedback loops are that are forcing them into these sort of idealized bankfull hydraulic geometries. And it just points to hydraulic geometry being a really powerful lever that can sort of skip over all the messiness of time varying discharge and time varying sediment supply. If we can get at what physical processes or physical mechanisms are determining the hydraulic geometry, then we have sort of a shortcut to predicting the behavior potentially of these rivers over longer time periods. And of course, it's not the first one to talk about it this way. I mean, people have been using hydraulic geometry for a long time, but traditionally in tectonic morphology, it's been sort of an empirical approach where we've noted these trends and fit them, but we haven't done so much to take the understanding that people have developed about what goes into these hydraulic geometry and adapt that to the landscape scale. And this really is spectacular, these trends. We're here, I've included rivers that go from steep, tiny little boulder-mantled torrents with channel widths on the order of a few meters, up to these massive lowland rivers with channel width on the order of a kilometer. And the discharge is varying by over a factor of 1 million in this data set. It's also, I think, kind of special. This is a data set that people have been compiling for a very long time, representing decades of work by so many people. First identifying which variables are important, and then going out and collecting all this data painstakingly. It's kind of a privilege that we're able to work with such an incredible data set, I think. Anyways, I just want to break it down a little bit. First, I have sort of separated the rivers in this data set into a couple different categories. First are gravel-bedded transport limited rivers. So gravel-bedded is anything where the median grain size is larger than 2 millimeters. And I have about 2,000 of these rivers. I call them transport limited if they were not explicitly labeled as bedrock rivers. So there are probably some bedrock or detachment limited rivers sort of hiding in this data set, but I don't have the resolution to pick them out. And then I also have sand-bedded rivers, where sand-bedded is just defined as anything where the median grain size is less than 2 millimeters. And I play a little trick here in the estimate of the roughness length scale, so this characteristic grain size D. So for the gravel-bedded rivers and the bedrock rivers, which I'm going to show in a moment, I just interpret the characteristic grain size as being the median grain size D50. And this is because this characteristic grain size, I think, conceptually, what it really most honestly represents is the roughness length scale of the channel. That's what I think is setting the length scale of the channel. And in a gravel-bedded river, the grains that are the D50 are traveling as bedload or just sitting on the bottom. These are the roughness elements that are what's producing the flow resistance. And even if they're not directly what's producing the flow resistance, they are the grains that are falling out of the flow, at those flow rates. So they're sort of still giving direct information about what the roughness length scale is. So here, that's what I use as the characteristic grain size. This is different in sand-bedded rivers. In sand-bedded rivers, so many fine-grained rivers, the sediment, like the D50 at least, is often traveling in suspension. The non-dimensional shear stresses are far, far above the threshold of motion. So and these are not the grains that are providing the flow resistance. Instead, the flow resistance is coming from bed morphology or bank morphology or something like this. However, if we know what the non-dimensional Shields number is, the non-dimensional shear stress is, it still provides an indirect estimate on the roughness length scale. So here, using this information, we can calculate what the size of the grain would be were it, just at the threshold of motion in these rivers. And I use that calculation so that the Shields number divided by the critical Shields number for bedload transport as a measure of the grain size. And if I do that, then these sand-bedded rivers plot very nicely on top of the gravel-bedded rivers. And the final component of the data set are some bedrock rivers there's not much to say about them. These are just explicitly labeled as bedrock rivers, and to first order, they follow the same hydraulic geometry as the alluvial rivers, and this is something that other people have seen before. That, yeah, I'm talk about it a bit more later. Okay, so that's the data set, and I'm just going to talk about how people have been, building up some pretty exciting theories for how we can, predict hydraulic geometry. Effectively, we create a mathematical model for a bankfull river, and the first element of this, the critical element to do this is to, so just to say, the goal is to really predict these response variables, the flow depth, the flow velocity, the flow width, and the bankfull channel slope as a function of the imposed sediment flux, water flux, and grain size. And I'm going to start just without sediment flux, so with channels that are not transporting any sediment. Okay, so the first element is a boundary condition, which really setting the shear boundary condition of the channel, the boundary condition at the actual channel boundary. And to sort of explain this a bit better, I'll talk about it in the context of the channels that I'm going to try to explain first, which is sort of the easiest channels are transport limited channels, so alluvial channels that are flowing, subform channels flowing through cohesionless sediment that are not transporting any sediment. And the boundary condition, the appropriate boundary condition in this case would just be that the shear stress on the boundary everywhere is at the threshold of motion of the grains. And so that if the shear stress is somewhere too high or too low, the channel is simply going to erode or deposit sediment until it reaches this state. And this is really an important step. How we determine or impose this boundary stress is really decides what the channel ends up, what kind of river we end up solving for. And later, when I talk about how we can invoke sediment transport, it's done by changing this boundary condition. And I don't know how to do it, but I suspect also, if we want to create, detachment limited rivers, it's going to be in this sort of the determination of how the stress is, the state of the stress at the channel boundary. Okay, the next constraint is conservation of mass, which is pretty straightforward, and then momentum conservation. So basically, we're just trying to solve for a channel which at bankfull flow conditions, has a channel boundary which is not eroding, which is a sort of constant. And in the momentum conservation, I include the lateral momentum flux, which is not something that's always done, but has been and it's an old idea that's been coming back. Basically, I would argue that the lateral momentum flux is just the friction that the water has with itself. And so if we have, water flowing in a channel, the water in the center of the channel is moving faster than the water on the sides, and it's dissipating some of its momentum on the boundary below it, but it's also indirectly dissipating some of its momentum on the channel boundaries, sort of the channel banks, through frictional interactions with the slower moving water on both sides. And this is accounting for that. And that's really what confers channels their two-dimensionality, I would argue. And this is in contrast to canal theory approaches, which confer two-dimensionality through a different process. And the final component is a constitutive relation, which just sort of describes how the flow deforms under an applied stress, and this is basically understanding the rheology of the turbulent flow. And for that, I use the logarithmic law of the wall, which is based on a turbulence closure. And in fact, I will use the turbulence closure, also the same turbulence closure adapted for the lateral shear stress. And so that technique of using the turbulence closure for both stresses is building on work by Shu et al. And this leads directly to an analytical solution for the channel geometry at bankfull discharge, which predicts the flow depth, the flow velocity, width, and slope as a function of the imposed discharge and grain size. And it's not the first person to do this. I think the model we've been working on is particularly nice that we've tried as far as possible to limit any sort of empiricisms or empirical scalings. And we've managed to do it almost with the exclusion of this turbulence closure model. And the channel model has just 5 parameters, and they're all independently measurable and relatively well constrained for terrestrial rivers. So we have the threshold of motion for these sort of non-transporting threshold channels. We just have the threshold of motion, the von Karman constant, the sort of a non-dimensional lateral momentum diffusivity, which is analogous to the von Karman constant. Then R, which is the ratio of the sediment density to the fluid density, and acceleration of gravity. So I would love to talk more about the details of this, but I don't think this is really the right place for it. And I'll just skip to the big picture. So we can plot based on just choosing, like, standard values for these parameters. I can plot then the predicted bankfull hydraulic geometry for these rivers against the observations. And I just want to say, because I use the logarithmic law of the wall to solve for the constituent relation, it means that this model is really only appropriate for channels where the flow depth is considerably larger than the median grain size. So this is maybe not something that everyone will be familiar with, but there are 2 really distinct hydraulic regimes that rivers find themselves in, depending on whether the flow depth is deeper than the median grain size or not, which I'll come back to later. And so this is the theoretical prediction here in the black dashed lines. And I just want to emphasize there are no fit parameters here. This is just what the model predicts based on standard values for these model parameters. And to first order, it would predict the trends of the hydraulic geometry parameters very well. But the trends tend to be offset, in particular for the width, the depth, and the channel slope. Actually, that's because I calculated the hydraulic geometry for channels that don't transport any sediment. And we know that with sediment transport, channels widen and shallow and steepen. And so that would bring this, if we had sediment transporting channels, would hopefully bring these predictions more in line with the observations. And conveniently, there's a very nice review about this that just came out, Phillips et al., which I can recommend reading. And here, basically, they break it down in just a way that's very convenient for me. Here, they have what they call zeroth order channels. These are just the sort of channels that I was deriving the hydraulic geometry for, where we have no sediment transport, and the boundary condition is that the shear stress is at the threshold of motion everywhere on the boundary. And what they're talking about is this idea that as we increase the sediment flux of a channel, we have a region that forms in the center of the channel where the shear stress is a little bit larger than the threshold of motion. So this is where the sediment transport is happening. And as a result of accommodating this extra transporting region, the channels widen a little bit. And as we progressively require more sediment flux, then the channels continue to widen more. And this is very elegantly confirmed with some beautiful experiments from a series of papers here, sort of La Jeunesse's working group, where they've sort of constructed laminar rivers in the lab. So these are not super physically realistic, but they have all of the critical components, which is sort of self-formed channel flowing through a cohesionless material that's also transporting sediment. And with their experimental setup, they can extract the river cross-sectional profile, which I'm showing here. So here you can see the little channel that they make. And in this first plot, this is a channel that's not transporting any sediment. And so you see the sediment transport rate is 0. And as they impose more sediment transport on these channels, you see that there's this transporting region in the middle. So the red line are the data observations, that this transporting region that forms in the middle of their channels here. So this is the transport that's corresponding to these channels. And the channels are also widening to accommodate this transport. And not only is this an elegant series of experiments, it's also some very beautiful theoretical work. And they build up, they build up in a similar style models of hydraulic geometry transporting channels. And so here you can see their theoretical predictions in blue, matching the river profiles and matching the sediment transport rates. And so using some of their ideas about how to invoke sediment transport in these bankfull hydraulic geometry models, I'm also able to adapt this to turbulent flow. So here's sort of the first results in invoking sediment transport by modifying the boundary stress condition of these channels. So here we have the channels that I first talked about that don't transport any sediment, and I'm imposing more and more sediment transport on these channels, and they're widening and getting less deep. And they're also getting steeper, but you can't see it from these cross sections. And this is just showing sort of a different overview. So here in black, in the black dashed line, they show the original theoretical predictions I made with channels that don't transport any sediment, and the red trends are the channels that are transporting sediment, and then they are indeed getting wider and deep, shallower, and steeper, as we would hope. But it's still a work in progress. Anyways, so that's kind of it for the hydraulic geometry models, but I just want to now come back to the landscape scale. And earlier I showed these river profiles, these long river profiles with this signature concave up morphology. So here we have our rivers that are getting less steep as we go downstream due to the increasing catchment area. And this satisfies this equation here where the product of the channel slope and the catchment area to some exponent equals a constant. And that exponent is referred to as the concavity index, and empirically, like in observations of real rivers, it has a value around 1/2. And it's actually well known that this comes from hydraulic geometry. So when we can sort of empirically fit these beautiful patterns that we see in the hydraulic geometry of real rivers, and using those empiricisms, then derive a sort of approximate model for fluvial erosion rate or fluvial sediment transport rate, and those empiricisms lead to this 1/2. So it's not really surprising that using this more rigorous sort of theoretical model of hydraulic geometry, that I can sort of extract the same slope area scaling. Indeed, the model predicts that the slope is proportional to the catchment area to some exponent, and that exponent has a range of 0.5 or 0.4 to 0.5 or so. But we can sort of go one step further, because it's not just an empiricism now, it's sort of a theoretical understanding, and we can understand what exactly the exponent is and under what conditions it changes. And also we can calculate what the coefficients of these relationships are. So here I'm just showing the full relationship between slope and discharge. And all of these constants are measurable, relatively known. And I just want to point out here, I think it's a really beautiful connection. The slope area scaling with its exponent of 1/2 is usually viewed in terms of a single river, a long river. And here we're seeing it in this data set of 3,000 different rivers, and showing their average trend also follows the slope area scaling with a similar exponent. So here's just plotting the slope against the non-dimensional discharge, which is effectively, the channel area. And the other, I think the key result is that, though it's still a bit preliminary, that the erosion rate, sort of the sediment transport rate, which is effectively just the upstream average erosion rate, is in these bankfull transport limited models. The theory that I was talking about is approximately, or not approximately, is proportional to channel slope. And so this is getting back to this original idea that was sort of an empiricism that maybe not empiricism is not fair, but this original idea that erosion rate or sediment flux goes with the average channel steepness, and we can sort of reconstruct it a little bit more rigorously here with these theoretical derivations of bankfull hydraulic geometry for steady state channels. Okay, so this is moving towards then rebuilding these profile models and river profiles with subsequent consecutive river cross sections that are sort of these rigorously derived hydraulic geometries, and already with, at least in the transport limited case, we can reconstruct the slope area scaling, which is a really key observation, and also that sort of reconstruct this key relationship that the erosion rate, and in this case the sediment transport rate, is proportional to the river steepness. And I mean, maybe it's very far away, maybe it's not going to happen, but I think that it sort of lays the groundwork for doing the same thing for detachment limited rivers. So a better understanding of how things are working at the hydraulic geometry level can then directly lead to a better understanding of how things are working at this long river profile scale. Yeah, what did I want to say about that? Just that, oh yeah, that's right. Exactly. Sorry, I lost my train of thought there. But one of the problems that often comes up in landscape scale geomorphology is that steady state river profiles of transport limited rivers or transport limited rivers, so alluvial rivers, are indistinguishable from those of detachment limited bedrock rivers. And so looking at steady state profiles is not informative when we want to understand the differences or the dynamics of these two different kinds of rivers. But potentially there will be differences in the bankfull hydraulic geometry of these two different kinds of rivers, even at steady state. And I think we don't actually see a lot of differences in several aspects of the hydraulic geometry, but perhaps in the channel slope, there are going to be some key differences, which makes sense if the distinguishing feature of these detachment limited and transport limited rivers is really the stress boundary condition that assigns, that constrains how the river finds its hydraulic geometry. Though it makes me wonder a little bit that these bedrock rivers, fall so nicely on the trend of the supposedly transport limited rivers, and really brings to fore this question of what makes a bedrock river or a detachment limited river. And I think there are some cases that are very clear, like the Fraser River, a big river going through a set of massive bedrock gorges in British Columbia, Canada. So here, the river is bound on all sides by bedrock, and very clearly the hydraulics here are distinct from an alluvial river. And there's no question that this is a detachment limited bedrock river. Here's a picture of me holding like the median grain size, and this is basically operating like sand in these rivers. It's truly spectacular, but I don't know if it's really so representative. And I think a lot more common in these sorts of landscapes, you find rivers like this that are maybe really operating as alluviated rivers in for long periods of time, or something sort of in between. They're sediment choked rivers. They're maybe not alluvial rivers, but I mean they're bound by bedrock, but they're not directly bound by bedrock. So I think looking at the hydraulic geometry is an interesting way to sort of try to understand better the differences. And I would expect that what we'll find is there are different kinds of bedrock rivers, and that maybe this blanket term is a little bit too general to really distinguish what's going on in these landscapes. Okay, anyways, just to finish then, one last little section, I just wanted to talk a little bit about what is going on when the flow depth is less than the grain size. So I said that the model I derived is really only appropriate for the case where the flow depth is larger than the grain size. And that's because we don't really understand the hydraulics, the flow hydraulics in this case where we have these rough channels, what we call them, when the flow depth is smaller than the median grain size. And I think it's relevant because a lot of the bedrock rivers and ostensibly the steep, rapidly eroding rivers are falling into this regime. And so, as I said, flow in this regime is poorly understood in general, but what we do know is that the flow velocity is slower and less intense, and that the threshold of motion is actually increased. So the threshold to move a grain is increased relative to other rivers. And this sort of combines to create a situation where sediment transport is significantly less efficient. And we can understand this by looking at, for a moment, back at the sort of more standard, or maybe not more standard, but the case where the flow depth is significantly larger than the grains. And in this case, a force balance on a single grain that's sitting on the bottom of this river looks something like this, where we have a gravitational force that's pulling the grain down onto the bed. And if it's tilted bed, maybe there's a small component pulling it downstream, but it's going to be small. And then there's a fluid drag force that's pulling this grain downstream, or rather pushing it downstream. And also a fluid induced lift force that's gently pulling this grain off the bed and enhancing its ability to be moved downstream. And then when we go to this other regime where the flow depth is small relative to the grains, and the grains start to emerge from the flow, all this changes. And to start, the drag force decreases significantly. So here, this is showing this in this data set of flume experiments from Lamb in 2017. On the right side are grains, the drag force of grains that are significantly smaller than the flow depth. And you can see then as we move towards the left, we're getting towards grains where the flow depth is smaller than the grain size. And as that happens, the grain size drops the drag force drops dramatically. And this is the same set of experiments, but I'm just showing the lift force now instead of the drag force. And what we see with the lift force is even more dramatic. It actually changes sign. So when the flow depth is large relative to the grains, the lift force is pulling the grain off the bed. But when we go to this sort of rough channel, shallow flow regime, the lift force changes signs and actually starts to pull the grain down or hold the grain down onto the bed. And the reason I'm talking about this is because flow depth and flows and channel slope are inextricably linked. So all else equal, if we increase the slope of the channel, the flow depth is going to decrease. And that means that in this conceptual model where we accommodate higher sediment fluxes and higher tectonic uplift rates with an increased river slope to drive higher erosion rates, we're inexorably moving towards this transition where the grain size is all of a sudden larger than the flow depth. And that's only going to be exacerbated if we're also generating larger grains in these more rapidly eroding landscapes. And I think this data set sort of shows nicely what happens in this situation. So here it's the same experimental data set with some field data from LAM 2017, where the channel slope is on the x-axis increasing to the right, and the threshold of motion is on the y-axis. And as we increase the channel slope, we also inevitably decrease the flow depth. So we're moving towards this threshold here, which I've outlined in yellow, where the flow depth is the order of the grain size. And there you can see the threshold of motion just increases dramatically at this threshold. So I don't have any sort of resounding conclusions here, other just to say that it's interesting, or I think intriguing that high slopes are associated with low transport efficiency and a sort of a critical change in channel hydraulics. And we're also seeing sort of this decoupling of channel slope and erosion rate at high erosion rates. One possibility is that as we're moving towards higher and higher erosion rates, more and more of the river network is in this alternative flow regime where the thresholds are higher, the flow is slower, and the sediment is all around less efficient. And it becomes the case that increasing the channel slope is no longer a viable mechanism to increase sediment transport rates or erosion rates. In any case, I think that it requires a closer look at the channel hydraulics. And that brings me to my conclusions, just that there's this intriguing decoupling of channel steepness and tectonics that seems to exist in some high erosion rate landscapes, and that using bankfull hydraulic geometry, we can maybe interrogate what's happening better in this alternative flow regime. Okay, thank you.
Thanks a lot for the very interesting talk. So the chat is now open for questions. And so feel free to ask your question directly in the chat, or to raise your hand if you want to ask your question directly. So maybe I can open with a question, actually.
Yeah.
It's taking the opposite problem. So as you nicely introduced the subject, one of the key points of using Kherson is that, or like channel steepness, sorry, is that with not a lot of data, we can get a lot of insight of what is happening in terms of processing on the landscape. So for example, if I see a sharp increase in channel steepness, one could see a nick point linked to lithology, tectonic, or things like that. So could we take the opposite approach, like if we have a value for channel steepness, how much of the parameters you've shown about bankfull hydraulics could we infer from that channel steepness?
I haven't thought about it too much. But I don't really think you can infer that much, to be honest. I guess you have the channel area and slope. If you know the area and slope to find the steepness, then maybe a bit more, because you have sort of a rough estimate of discharge. But I think a missing component often is the characteristic grain size that sort of sets the scale of the whole problem. And unfortunately is something that is not so easily viewed from, DEMs. But I think that, yeah, so.
Thanks. I may continue with another question. It might be a bit niche. Oh, we have a question in the chat from Kristen Cook. How might this change in channel steepness erosion rate compare to a change in hill slope erosion rate process? Could this be where landslides start to be important?
Yeah, that's actually my favorite idea as well, Kristen. I don't really know what's going on in these landscapes, but I thinking about it a lot, and it seems like landslides are a very likely candidate, but it would still need a mechanism by which landsliding all of a sudden induces this dramatic change in the behavior of the rivers. And I think that in supplying much larger grains to the rivers suddenly might be that mechanism, but would still require a better understanding of the channel hydraulics. Yeah. Yeah, exactly. So Kristen just said that, yeah, I guess everyone can see that the large grain is exactly my thought. And I think a lot of this is probably a grain story, but who knows? I mean, we just have to go take a closer look. And people are doing that. There are so many new tools available to take a closer look at channels. I think a lot of this stuff is going to start to sort of become clear in the next years.
How much of the perfect shape of the channel you have relies on steady state for the bankfull hydraulic?
I think, sorry, can you say it again one more time?
Yeah, sorry. So you mentioned that the relationship you're describing is close to kind of make the assumption of steady state, right? Or maybe I did not get that.
Yeah, sort of a channel scale, like a cross-sectional steady state, yeah.
So we have a lot of systems in transients, which we have like the same problem with having the slope area relationship. But how much could you does that hold when you have like transient hydraulics in your system? Or I guess my question is more about like, can we consider this valid when we are averaging long-term channel like geometry, where you can have quite a lot of hydraulic variations during that time?
Yeah, I think that I don't really know much about the transient case. I think it gets a lot harder, but I think that it's also very short-lived relative to what's going on at the landscape scale. So for alluvial rivers, they seem to reorient and reach new steady state very fast, and it might be that they are almost never that far away from steady state. And I think just the fact that all these rivers pretty much plot, with definitely some noise, but plot on this trend is indicative of how strong the feedbacks are that are keeping these channels near the steady state. So I think if you try to talk about transient channels, it maybe gets a lot harder, but I really don't think you need to. I think you can have a transient profile where most of the river is still at a steady state in the hydraulic geometry perspective.
Which is a good news if we don't want to deal with complex hydraulic, I guess.
Yeah, exactly.
Right. So we still have time for a couple of questions if anyone has a last one. Otherwise, thanks a lot again for this great talk. It has been recorded, so it will be uploaded on YouTube as soon as possible.
Okay, great. Thank you very much.
Thanks again. Thanks again for giving this seminar, and we will see you all next week for next Landscapes Live.
Okay. Bye-bye.